Hey YouTube, what's up? It's Link. Welcome back to another episode of Coding Session. And today's gonna be a little bit more of an interesting video. So since we've been doing binary tree episodes for the past few episodes, I completely forgot about two important traversal algorithms, which is the depth first search and breadth first search. This video is gonna focus more on depth first search, and I'm actually gonna show you an application for it. So this is gonna be a preview of some code of an open source project that I am currently participating in. So with my capstone, or should I say senior project classes, I've been given a wonderful opportunity to be part of the Amylite research organization at FIU and work on the open source software defined networking platform, or SDN, which is Ketos. And I'm part of a team, and as a team as a whole and as a team member, we're responsible for working under the Agile Scrum methodologies for designing, implementing, and testing bug fixes for the platform itself, improvements to current features, and even designing and implementing and testing brand new features for the platform. And this semester's focus is mainly on designing a brand new feature for its Pathfinder component. Whereas last semester we were getting familiar with the platform, fixing bugs, improving, making small improvements to current features, and adding very simple new features. But this semester's focus is to create a brand new feature for its Pathfinder component. In short, what we have here is a network X graph that has nodes and edges, users, and switch nodes, and each of them have a weight, but not necessarily weight, more of a metadata to each of its edges, which is a delay. So our goal of this semester is to create a brand new feature in the Pathfinder component to find an exact path based on a user's specified propagation delay. So at the beginning of the year, we had the spring semester team develop a shortest path algorithm for its Pathfinder component, but now we have to go ahead and make a exact path algorithm. Last semester it was a team of 4, and this semester it's a team of 5, and that 5th team member is actually one of the members who created the shortest path algorithm back in the spring semester. He's currently taking his grad classes and has had the opportunity to join us as a team to work on this project. And I'm going to leave a link down below to his network X, his exact path example using network X, because this code it's based off it's the depth first search function. This is the one that he developed for us, and I just did some small modifications to it. His name is Marvin, and of course, out of all the team members, he's the most experienced when it comes to this project, and Ketos and Network X itself. So he's been a big help. Definitely recommend you check out his example. Again, I'm going to leave a link down below in the description. But this is pretty much his, just with small modifications made by me and my other team members. So first off, before we get started, let's go over the depth first search algorithm. So the depth first search algorithm is similar to a traversal, and you're pretty much traversing through a tree or a graph. And of course, a graph is a little bit different because there's many cycles in a graph, and a node may be visited twice. So there's, especially in an application like this for the Pathfinder, this is no exception. And the depth first search is pretty much an algorithm, again, searching a tree or a graph, and it starts at the beginning of the root node and goes as far as possible, traverses as far as possible as it can before backtracking. And even if you find what you wanted to find in your first search, it's going to backtrack and try to find all the possible avenues. And that's where recursion comes into play when it comes to depth first search. That's how powerful it is. So I'm also going to leave a link down below for the Geeks for Geeks for this. with a set of code and explanation, definition, and more in-depth information on depth first search. But I'm going to go over some code from the project I'm working on. So we created a network X graph, which network X is just a Python library that you can go ahead and create graphs like this, have some nodes, add some edges, add some weights to it, or even add metadata to it. In this case, we added delay to it. These are just getters and setters. Just getters for debugging purposes. So this adds the nodes to the graph, define the edges, and their metadata, which is delay. Put that in a list, and then just simply add them all. And this is where the recursive functions come into play. So this is a wrapper function for this, so we can start at the beginning of the graph. And what we want to do in this test is find a path between user A and user B, but we want to have that path have a total delay of 29. So we have some base cases here. So let's go over this for loop first, because these will make sense after we go over this. So for each neighbor, and I kind of read these for loops like that, like for each, so it's easier for me to actually read it. So for each neighbor in list self.graph.nodes current, so the current node we're on, we're going to get each of its neighbor adjacent nodes, put them in neighbor, and of course with each execution, which is where the recursion comes into play, we're going to manipulate it in some sort of way. So we have edge delay, and we pretty much get the delay of the current node we're on and its neighbor node. So think of it as the delay of the current traversal, of the current edge we are traversing, such as what we're doing, user A. So user A to S1, 3. 3 is in here. And of course we want to append that edge. We want to append that edge into our path parameter here, which is of list type, because once we find a path, that's going to be the data type it's going to be, which is a list. And then here's where the recursion comes into play. Delay minus edge delay. Now this delay is delay 29, or whatever delay we specified and passed through our wrapper function here. So 29 minus 3, which is 26, and now we have delay of 26 remaining, and we want to go ahead and keep traversing through edges until we get our delay to 0. And of course we pass in the neighbor node, which is going to be the next current node, and of course targets pretty much stays the same, and then path stays the same, because as we're recurring through the depth first search function, we're going to append those current traversed edges, but if we reach a dead end, or an end was reached, we're going to start traversing back. That's what depth first search does. It goes as far as possible into the graph before traversing back or backtracking, and we want to go ahead and remove those edges so we can clean up our path list parameter, so that way once we backtrack, we're going to have an empty list, so that way we can build a fresh new potential path based on the propagation delay we have specified. And now to go over the cases, of course I've already hinted at it. If we do find the path, eventually as we're subtracting 29 minus each edge we're traversing, it's going to reach 0, and if the current node we're on is equal to the target's node, print the path. But if we go below 0, if we go below 0, that means the path that we have created has a delay more than 29, and simply just return and start to backtrack to find other possible avenues in our graph. But there are also cases where you might not even reach 0 or even go below 0, and it's too short. and of course it's going to start to backtrack and do what it has to do, which is backtrack all the back all the way back and start to find all other possible avenues. So that is the power of the depth first search algorithm and the power of recursion when it comes to this algorithm. Start at the root of the graph or the tree, explore or traverse through the graph or the tree as far as possible before backtracking. But if you find what you're looking for, the depth first search algorithm is still going to backtrack and find all possible avenues. Alright, so let's run our example here. We want to find user A to user B with a propagation delay of 29. As we see here, it's found it. User A to S1, S1 to S3, S3 to S5, S5 to user B. So let's add that up. User A to S1, which is delay of 3, S1 to S3, so that's 13 because that delay is 10. S3 to S5, 13 plus 12, that is 25. And then S5 to user B, which is 4, which is 29. So it found the exact path that we were looking for. Now I want to go over, I don't know why that's not closing. Now I want to show an example of the depth first search algorithm actually finding what we're looking for, but it's still traversing back so it can find other possible paths or avenues. I think this is an example, and I know it's kind of a poor example in this application for exact path, especially for the Pathfinder component in Ketos, but just for this prototype, which is what the product owner wants for now, so we can have some code to play with when we start to implement it into Pathfinder. We can go ahead and find user A to user A. That's perfectly legal. With a desired delay, I changed it to 12. And as you can see here, we have two lists this time. Let's go ahead and look at those. So as you see, one of them is just ping-ponging back and forth. User A to S1, 4 times, 3 times 4 is 12. And this one is doing, the second one is doing user A to S2, which is 6, and then S2 back to user A, which is another 6, that's 12. 2 times 6 is 12. So that's just an example of the recursion power of this depth first search algorithm. We found what we're looking for, but it traversed all the way back and started to, or sorry, it backtracked. I should say backtrack, not traverse, because that kind of gets confusing with the terms. It goes as far as it can, finds what we're looking for, but backtracks so it can go ahead and traverse and explore other possible paths or avenues. So that is the depth first search algorithm, what it is, how it works, especially with the power of recursion, and also a preview of some code of a project or an open source project I am involved in. And of course an application for the depth first search algorithm. So hope you guys enjoyed this video. I recommend checking out Marvin's GitHub repo for the network exact path prototype down below. This wouldn't have been done without him. He's been helping the team out wonderfully. I think without him, we would definitely have not made the progress we have now. He's a fantastic team member, so definitely check that out down below for his prototype. And also, I will leave a link down below to the Geeks for Geeks. I don't really want to call this an article, but just a page with information of the depth first search algorithm, along with some examples in C++, Java, Python, and C#. So, do apologize if this video was a little bit long, but since I was explaining not only the algorithm itself, but also showing you and explaining a implementation of it to an actual application, which is the Pathfinder component in the open source project I'm participated in. showing you guys the application. Of course, it's gonna take a little bit longer for the video. So yeah, so thank you guys for watching, and any comments down below? You want me to explain something or make things a little bit more clear? Definitely will try my best. So yeah, have a nice day. See ya.